All right, good morning, everybody. Welcome on in. We're going to get started here with some Math 3 material. So most of what you've seen so far in this class, or the first chapter, you should have at least been exposed to that before, and probably you've seen some systems of equations before, but we're getting more into a situation where, this class will start expanding more and more into the types of problems that you probably have not seen before, or if you have seen them before, you'll be doing them at a much harder level than you did before. So for instance, systems of equations. You may have done some systems of equations before, and that's great. That's going to give you a great introduction into this chapter. We probably will be doing systems of equations that are more complicated than what you've seen before, right? So that's not to intimidate you or to scare you, just to kind of let you know that's kind of how a lot of this class goes, which you've seen much of this stuff before. Some of it you haven't. Some of it you may have seen before, depending on what school you went to. But we're probably also doing it at the problems get a little bit more harder than you saw before. So like if you took Math 1 here, beginning algebra at the college, we did systems of equations at the end of the semester, but they were a little more basic problems just to kind of help you get the hang of systems of equations. Whereas here, you're going to be doing problems that are a little bit more difficult, right? A little bit more difficult to do. So just be aware of that. Also, there's still a couple people, and I'm sure they're not in the room right now, but I'm just putting it out there so that everyone is notified in time. There's still a couple people who have not done anything or very, very little in regards to this class so far. As a reminder, I'm contractually obligated to drop those people, so I'll be doing that tomorrow. So when I look tomorrow, if you have no assignments done, you're definitely getting dropped. If you just have a little bit of assignments done, probably getting dropped, depends on how many you've done. So the best case scenario is that you're more or less caught up, right? Some of you are completely caught up. Some of you are like, it's understandable if someone's slightly behind. Then I can make an argument that, no, this person is, sure, they're a little bit behind, but they're obviously making an effort to be successful in the course. And even if you kind of go the next 16 weeks slightly behind the whole time, that's not good. That hurts, but you probably will still finish the course successfully as long as you kind of catch up at the end. But if you're significantly behind, then my deans want me to drop you. And that's what we're obligated to do. So just be aware that'll happen once you get dropped from the class, unless I've made some type of terrible mistake where sometimes when we're putting stuff in our forms, like the drop-down stuff, sometimes you accidentally can grab a wrong name or something like that. Unless you were dropped for a mistake, you won't be reinstated into the class. Like if I make a mistake and you've done all the homework and I accidentally picked your name instead of the person above you on the list on accident, then we'll get you back in the class. But if you were dropped for doing no effort, it won't do any good to come back later and say, oh no, now I'm ready to do a bunch of work. Unless you were dropped for a mistake, you're not going to get reinstated in the class, right? So just be aware, tomorrow I'll be doing that for all 3 of my classes that have started. 2 of my classes haven't started yet, and they run on different time frames. But for the 3 classes that started, I'll be doing all those drops tomorrow. So just be aware of that. Before we get into new material, is there any questions? I know we spent a bunch of time on piecewise functions before. I haven't heard any more questions since then on anything, so I'm kind of assuming that people are okay with the material. If not, let me know. Again, you can always shoot me a question in an email or a screenshot of a problem or some kind of thing, which I can, address in the next class. So you're always welcome to do that. Okay? All right, I don't see any questions popping up, so we will move into the new chapter, which is systems of equations. Like I say, most of you have probably had at least some exposure to systems of equations, although it might be very, very small exposure, right? Okay, so a little confusion on piecewise functions. Yeah, so if you want, feel free to hop into office hours when those are available, and I can certainly help you out on a one-on-one basis if people are still confused on that. So Yeah, so we'll move ahead. Basically, I'm going to introduce systems of equations to you. It's one of those things that seems confusing, but then once you get the hang of it, you just kind of can do every system of equations that people throw at you. Okay, you can just, they're kind of all the same once you get the hang of it. There's a few different methods, and I know it can be a little confusing and overwhelming at first. We've got the substitution method, we've got the graphical method, we've got the elimination method. But at the end of the day, you get to choose which of those methods you want to do, right? A homework problem may say, solve this system of equations using substitution, but it really you just need to be able to solve systems of equations, right? Which is an important task. A lot of times people think, well, I've never had to actually use systems of equations. Why is this all that important? But that's how a lot of mathematics works, is people think because they don't use it, that it's not important. But the reality is many people should be using a lot of this mathematics, right? Using it in the workplace, using it for their own lives. Sometimes systems of equations come up. Systems of equations actually gives rise to a whole area of mathematics called linear algebra. Linear algebra is one of the most used areas of mathematics there is, right? Your phone, although you don't know it, your phone is solving systems of equations inside of apps at different times in order to figure things out. There's lots of things that power our world where systems of equations are being used right now. You would be hard-pressed to find a business or an area of research or someone who's calculating stuff where systems of equations shouldn't be used somewhere in there, right? In other words, they get used all over the place. But mathematics is one of those subjects, or it's the subject, where people think it's kind of okay to not use certain stuff, but it can be helpful in your life, right? It's like people are fine to go buy a car, and then whatever loan the car dealer wants to give them, they just sort of sign it and don't look it over. But you should be looking those over. You should know how to crunch the interest rates and what how much you're paying in interest and all that kind of stuff. People don't, and people go, well, I don't need to figure out interest. What's the big deal? Well, most of those people are also paying too much for their cars and stuff, right? You can ask most people who know mathematics. When you go to buy a car, the loan they give you, you first look at it and go, this is ridiculous. There's no way I'm taking this. And then there's usually like a better deal that comes up. So you kind of have to, if you're math illiterate, you're going to miss out on those opportunities to do better for yourself. This is one of those things. Knowing how to do systems of equations, you're not going to use them in your everyday life, but when you do need to use them, they can be extremely, extremely helpful, right? So let's get into them a little bit. And also, I know it's weird because a lot of the problems that you're given to do, like the word problems for systems of equations, they seem ridiculous. You're like, I would never want to do this, right? Why would I ever do a problem like this? But keep in mind, the reason for that is because we're giving you simplified versions that you can do as someone who is first learning systems of equations, right? In the real world, if you were at your job and you had to calculate a systems of equations, it probably wouldn't just be two equations and two variables. It would probably be much more complicated than that, and we're not quite ready to tackle that. You're kind of learning the basics of systems of equations, and that's why when you read the problems, they can seem ridiculous. Like there'll be problems where like, this cookie has this many calories and this candy has this many calories. So like, and it's like, you as a real person, who cares, right? For a problem like that. But do realize there's an importance here that systems of equations get used in every area of business and science and all that kind of stuff. Okay, with that said, let's jump into it. So when we talk about a system of equation, and specifically right now we're talking about systems of linear equations, so that means we're talking about lines, okay? Or when we talk about the three-dimensional case, we'll be talking about planes. A plane is like a flat surface, like a window is a plane, that kind of plane. Those of you who end up in, say, a pre-calculus or a college algebra or something like that, you'll end up doing systems of equations that are nonlinear. For this class, we're generally concerned about what's called linear systems of equations. Okay, and those are a little more, that's more standard. That's what you're more likely to run across in real life. Excuse me, is systems of linear equations, and like I say, it gives rise to a whole area of mathematics called linear algebra, which is very helpful. So, A system just means a collection. So when we say a system of linear equations, we're really talking about just a fancy name for saying we have a grouping of linear equations that we want to know about. Okay. Now, the difference about a system is that we want every equation in our system to be satisfied. Okay. You're used to having one equation, and when you have a point or a solution, you need to verify that it's a solution to that one equation. But now we're talking about having, say, two equations. I have two equations, and I want to find a solution that satisfies both of those equations. I want them both satisfied. Okay, so that's a little bit more complicated to do. So let's remind ourselves what even a solution to one equation is. So let's take y equals 2x minus 1. So there's a line. So we have a linear equation here, and it graphs as a line. You remember how to graph these, hopefully. You've got your slope and your intercept and all that kind of stuff. Well, what does this line really represent? Well, this line, as we look at it on the graph, is a graphical representation of all of the solutions to the equation y equals 2x minus 1. So how many solutions are there to the equation y equals 2x minus 1? Well, there's one for each point on the line, and that's an infinite number of points. So there's an infinite number of solutions to this equation. Each of them is represented by a point on the line. So let's say I wanted to find a solution to y equals 2x minus 1. Well, I just look at my graph and say, what about this 1, 1, this point 1, 1? Is that a solution? Because we can see that's a point on the line. Well, if I plug that into my equation, so plug in 1 for x and 1 for y, what do I get? I get 2 minus 1 equals 1. Yeah, that's true. So see how that x and y value together satisfy the equation of the line? Right? And we could pick another one. Why don't I pick another point? How about 2, 3? That's another point where my x is 2 and my y is 3. Now, if I plug x equals 2 and y equals 3 into my equation, what do I get? I get 4 minus 1 equals 3. Yeah, that's true. So see how any point we grab here and we plug it into the equation, it makes this equation true? That's what the graph of a line is. It's a visual representation of the solutions of a line. Hold on one second. I got to plug my iPad in here. Or otherwise the Zoom call is going to drop at some point. There we go. So, and all these points, see how I picked these two? All the points in between would satisfy it too, but these are harder because they're all like fractional and decimal, so they're really kind of ugly answers to deal with. But you want to remember, these are all points on the line too. We could plug these in and they should work as well, right? So we have an infinite number of points satisfying this equation right here. That's what a single line is. Okay, so what about when we get a system of equations? So now I'm going to add a second line, and we want to know the points that satisfy the entire system. I no longer care just about the points that satisfy this line. I want to find the points that satisfy both lines. So let's go y equals 1/2 x. Oops, I meant negative 1/2 x plus 4. Here we go. So now we have this new purple line. So let's ignore the red one for a minute. But the same reasoning that we just gave about what a linear equation is can be applied to the purple line, right? Every point on this purple line represents a solution to this equation right here, y equals negative 1/2 x plus 4. Okay, so then how could I go about finding a thing that's a solution to both? What you wouldn't want to do is say, well, let's take that point we found over here. How about 1, 1? I know 1, 1 satisfies the first equation. Is it going to satisfy the second one? And then you could just try all the solutions from the first equation and plug them into the second equation and see if they work. Except that's not a good way to do it because there's an infinite number of points on each of these lines. So you don't want to be plugging in an infinite number of points, right? That's not a way to get to your answer. So what can we do? If we want to find the solution to both of these equations, well, graphically, it's pretty easy, right? So that's why we start off like with the graphical method for systems of equations, because most of the time students can understand it pretty well. It's conceptually easy to understand. Unfortunately, we don't usually use it that often because it's not good with messy systems of equations. I'll give you an example of that in just a moment. But This graphical method helps you understand what's taking place. And then once you do that, we get into the algebraic methods. Most of the time that you solve a system of equations, you will be using the algebraic methods. However, it's easy to get bogged down in the algebra and forget what you're doing conceptually, right? So the graphical method is really good for understanding conceptually. The substitution and elimination, which we'll get to today and next time, and probably even after that, those are good ways to actually do the problems, right? And some of you are going to find in the future you actually have to, programming is becoming more and more a part of the future. In fact, programming is going to be one of the last jobs that's replaced by software and robots. So more and more people are going to find, that they have to do at least a minimal amount of programming. It's very common when you have to program something that you're going to have to come up with being able to do some basic programming to have it figure out a system of equations. That's not rare at all. So if you understand the system of equations, that's actually not very hard to do. If you don't understand system of equations, that's a little harder. Some of you will have to do that, some of you won't. Okay, so let's just review. If all the points on this red line are the solutions to that equation, and all the points on this purple line are the solutions to that equation, then how could we find a solution to both equations? Well, that's what we call the intersection, right? Right here. This point right here, 2, 3, that's the only point that lies on both of these lines. Well, I've stated a few times now that a point on a line is a solution to that equation. So if this point of intersection, that's a point on both lines, therefore, it must be a solution to both equations. And sure enough, if we plug it in, so let's take 2, 3. If I plug x equals 2 and y equals 3 into this first equation, I get 4 minus 1 equals 3. Yep, that works. Let's plug it into this bottom one. So if I plug in 2, I get negative 1 plus 4 equals 3. Yeah, that works. So it's very easy to verify your system of equations is correct. It's harder to find it, right? This is true a lot of times in mathematics. It'll take a bunch of work for you to find the solution, but once you find the solution, it's very easy to check. Okay, all you have to do is plug it into both of the original equations. If it works, you're good to go. That's much faster than having to redo a whole new problem because you missed one on Delta Math, right? Taking 15 seconds to check your work is better than doing a whole new problem in order to get your point back, your score point back on the Delta Math, right? So I highly encourage you to check your work there. So graphically, when we graph these things, it's easy to find a solution to a system of equations. It's just the point of intersection. And this is part of the conceptual part that we want to keep this in mind, because we're also going to bring up some weird solutions that we get in a little bit here. And you want to be able to have these 3 images in your head, right? This is the common one. This is what you're going to run across probably 95% of the time. Maybe 80-90% of the time when you're doing these problems. You're going to get this. You're going to graph 2 lines. You're going to get a point of intersection. That's your solution, and you're good to go. So you should just kind of have this in your brain and go, okay, yeah, that's right. I remember him doing that in class. That's what this solution is supposed to look like. I'll show you what the other solutions look like in a few minutes when we get to that. But you want to have each of those images in your brain so you can go, oh, this is the one where they're parallel lines, or this is, whatever the image is that you're working on. For right now, it's going to look something like this. Okay. Now, why don't we just use graphing to solve all systems of equations then? And here's why. See the problem? A moment ago, our solution ended up right on a nice grid point when we had it like this. See how the solution's right on a grid point, and it's real easy to see? That's 2, 3. Very easy to see what that solution is. If I change this, what is the values here? It's a little harder to see. So as I zoom in, you can tell it's taking place in the middle of here. It's hard to see exactly what those values are. And sure, if I hover over it, it says 1.6 and 2.2. But there's a good chance for a lot of problems that those are not the actual values. Those are approximations of the value. For instance, if we did this, if we made that 1/3, we'd really be in trouble. See how we're getting kind of ugly numbers here? It's just rounding those off at 3 decimal places. The solutions to this are not 1.714 and 2.429. If you calculated them and put them in a calculator, you'd actually see, your calculator would give you like 10 digits and then give up. So actually there's a big long number, and the real answer probably goes even further than that. There's a big long number that's being cut off and rounded right here. You might go, well, isn't that good enough? Usually not. In mathematics, we want to have exact answers because it may make a big difference, right? If this is your business and you're trying to maximize profit and you're trying to figure out how many units you should sell to maximize your profit, you don't want to know kind of roughly how to maximize profit. You want to know exactly how to maximize profit, right? And you might go, well, if we're going 3 decimal places, isn't that enough? Well, what if the units you're using here is tens of millions of dollars? Then 3 decimal places is still going to be what? Hundreds of thousands of dollars. If you're running a company, don't you want to be exact enough that you're not leaving hundreds of thousands of dollars on the table? You want to capture all that money as best you can, right? Or if you're trying to create some technology, you don't want to be the company that's, their values are pretty good. You want to be the company that's like, you do the work right and you're getting the best value out of the technology you're creating. So estimations are not good enough. We want exact values. That's where the graphical method fails, and where the algebraic methods, which we might get into the algebraic methods today, but we'll definitely be talking about them next time and probably a little bit today. That's where those methods come into play, is finding the exact values. Okay, so just keep that in mind. If you're ever doing the graphical method on a system of equations and it comes out kind of messy like this, it means you should be switching over to one of the algebraic methods that we'll be learning later. Okay, so we just established that for a system of equations, the intersection point of those 2 lines is the solution to the system of equations. The solution you come up with will satisfy all of the equations in your system. Okay, well, let's play around with that a little bit. Let's change this. What if I had a system of equations that looked like this? Y equals 2x minus 3. So here's a system of equations. It's a totally legitimate system of equations. I've got 2 equations here. And these are what? These are parallel lines that do not ever touch each other, right? They have the same slope. I could come up with we can come up with lines that look parallel, like that. That looks pretty parallel, but when we look at the slopes, we go, well, this has a slope of 2. This has a slope of 1.9. Eventually, if we zoom out far enough, these lines are going to cross each other. But if the lines have the same slope, then we know those are parallel. They're never going to touch each other. It's like train tracks. They just kind of go off to the distance, and they never run into each other. Why is it doing this? I turned off the automatic hand raising, and it's still trying to make me do it. What happened here? Sorry, let me change this setting. It's been doing this weird thing with the... They put in a new thing where if I show my hands on the screen, it raises my hand automatically for me, which is annoying. And I turned it off before class, but somehow they turned on again. So let's turn those off. Okay, sorry. Hopefully I won't get distracted by that again. So 2 parallel lines. So we've decided that the solution to a system of equations is the intersection point of those lines. Well, this system right here has 2 parallel lines. There is no intersection. So what is our conclusion? What do we conclude if we think that the solution to a system of equations is the intersection point? The system that we're looking at has no intersection point. Well, then it follows that there is no solution to the system of equations. So this is a case where you would say no solution. So there's 2 ways that happens sometimes. Sometimes you can just write no solution. And off the top of my head, I don't remember what they do in Delta Math. I'd have to go back and take a look again. But sometimes no solution, that's a reasonable thing to do. Sometimes we use what's called the null set, which I think there's a big push in mathematics right now. Let's see, that might be the wrong. I have to remember the command for the null set. Is it empty? Hold on one second. I forgot the command here. empty set. I see. There we go. Put it on a different line. There's a big push right now in programs and mathematics to push a lot of high-level notation into the algebra, which I think is a misguided attempt. I'd rather students understand the concepts rather than memorizing symbols. But see, this looks like, to many of you, this probably looks like a 0 with a line through it. In mathematics, that circle with a line through it, or the 0 with a line through it, has a very special meaning. It's what we call the empty set. It means that in this case, it means the set of solutions is empty. There is nothing in the solution set, therefore there are no solutions. Okay, so these two things in this case mean the same thing. All right, so just pay attention to, like I say, off the top of my head, I forget how Delta Math has you do it, but just pay attention to and be ready to use either one. In mathematics, like a lot of times you'll see people who do like accounting and stuff like that, they'll write their zeros with a line through it. In mathematics, we don't do that because that symbol is already used for the empty set. So this doesn't mean 0. This means no solution. Okay, a 0 should just be like a circle with no line through it. That's how you should write 0. And people then get confused and say, oh, does that mean that 0 is the same as no solution? Nope. 0 is a legitimate number. It can be a legitimate solution. The empty set means a set with nothing in it. When it's a solution set, that means your set of solutions has no values in it. That's not the same thing. Like you can have $0 in your bank account. That's a legitimate solution to an equation, right? So just keep that in mind. That's what those symbols mean. Right. So this is the second picture that you should kind of have memorized. And when you're doing a problem, this picture should pop up in your head and you go, oh, this is like that problem where there's two parallel lines that never touch each other. Therefore, there's no solution. Okay. Therefore, there's no solution. So you should, just sort of like stare at this for a minute and go, okay, that's the second one I need to memorize. Because like I said, once we get into the algebra, it's really easy to like forget a lot of this conceptual stuff that we've been looking at. And what I see students is confuse their answers, especially the one we're looking at now and the one we're going to look at in a minute. They'll do all their work correctly, like all the algebra, and then their conclusion's wrong, right? Because they mix up the second and third of these pictures. But if you stare at it and you understand why these parallel lines have no solution, because they have no point of intersection, you're much less likely to mix them up. Okay, so this is, every chapter probably you're going to hear me talk about this. Don't worry about memorizing everything. Worry about understanding things. If you understand things, you're not going to mix up the solution. If you try to memorize things, you're going to end up, at least part of the time, writing an infinite number of solutions here when the true answer is no solution. Okay, and that's a big deal. Concluding that there is no solution is very different than concluding there's an infinite number of solutions, which we haven't talked about yet. We'll get to in just a minute, okay? Okay, so we saw the situation where we had what happens most of the time, which is two lines that cross at an intersection point. That intersection point is your solution. We've now looked at this case where we have two parallel lines that are never going to have a point of intersection. Well, what if we had this? Oops, 2y plus 2 equals 4x. Oops. There we go. So these two, let's not look at the graph for a minute. These two lines that I have written here algebraically, they look different, right? If I handed you these, you'd go, yeah, okay, you gave me one line, and then you gave me a different line. That would be your assumption, except I didn't. What I gave you was the same line in two different forms. And that's going to happen sometimes in your systems of equations. Is your system of equations will actually be built from two of the same line, but you won't recognize it right away. Because it's totally reasonable when you look at these, you go, I don't think they have anything in common. And you move on. But look what happens. When I graph one and then I graph the other, look, it's right on top of it, meaning that these are actually the same line. If you took this second equation and you solved it for y, you'd get the top equation, okay? So it's just two ways of writing the same line, but this is our third type of outcome. This is what we call a dependent system. The first two situations are called independent. This situation is called dependent. Okay, so they're dependent because one of these lines depends on the other line because it is that line. It's actually the same line, so it depends on it. This will make a little bit more sense when you get into larger systems of equations, but we only do a little bit of that in this class. So, well, let's think about it in terms of the reasoning that we've been given so far about how to interpret our systems of equations. Well, we said that the points that are solutions to a system of equations are the points that lie on both lines, right? Well, which points lie on both of these lines? Well, every point on the line lies on both of them, right? Every single point on one of these lines is shared by the other line because they are the same line. They are literally the same line. So what that means is every single one of these points on these lines here are a solution to the system of equations. They're all solutions. And that might sound like a good thing. Occasionally it's useful. A lot of times it's not helpful. It means you got to go back and maybe look at the way you set things up. And you might think, well, in the real world, why would I set up a system of equations that has the same line in it twice? And the answer is you're usually not going to on purpose. It happens on accident. Maybe there's part of your company about your manufacturing system that pops up in a few different parts of your manufacturing. So you look at you look at the the packaging, the part of your company that's processing the packaging, and you come up with an equation for that. The part of your company that's processing the actual part that you sell, you come up with two different equations. Well, it could be that there's something in your business that affects both of those. And so when you come up with your equations, you accidentally go, oh, I just got the same equation both times. You've created a dependent system, and it's going to look like this. Right? A lot of times they look a little bit more complicated than this, like I say, when we get into more equations and more variables, but we're starting off real simple so that you can just understand the basics and then go from there. So, right. So it makes sense that there's an infinite number of solutions to this equation, and they are all the points that lie on this line. Now, here's where there's been a bit of a change, and I think this is actually a good change into the way they used to teach this to the way we teach it now. It used to be that books wanted you to say, oh, there's an infinite number of solutions. But that's not really a good answer, because think about the first problem we did when we tried to find that single solution. We didn't end by saying, oh, there's one solution. We said what the solution was. Right? That's not helpful to you if you're running a business and you tell your accountant, okay, can you go figure out the optimal profit that we can come up with? And your accountant comes back and says, yep, there is a solution. There is one optimal amount that we can run to maximize profit. And you go, great. What is it? And they say, well, no, I'm just telling you there's one solution. I don't know what it is. That's not really very helpful, right? So when we did that problem, we found the solution. We didn't just count how many there were. We found it. And then, yes, when there was a problem with no solutions, we said there aren't any, but there's no solution to state in that case. In this case, it's not really good enough to say there's an infinite number of solutions, even though some of you may have previously learned to do that. That's kind of the old method of the way this kind of stuff was taught. Yes, there's an infinite number of solutions, but what is one, right? You want to be able to represent what those solutions are. We're not just counting how many solutions there are. We're trying to give an indication of what they are. Now, this is where some people can get a little bit confused. So there's a specific notation that we use, and it's new notation, but you just kind of want to learn it. So let me show you. Mathematics has been restructured to be taught and understood from set theory. This wasn't true like 200 years ago. This was kind of early 1900s. Mathematics was kind of fraying because they had all these different countries were working on it, and they kind of unified it and said, let's redo our mathematics, same information, but let's build it from a common place that we're all sort of understanding mathematics in the same place. And at the base of mathematics, there's what we call set theory. So sets are very, very important in understanding mathematics. Like I just told you a little while ago, this symbol right here, that actually represents a set, right? It is the empty set. So if your solution set is empty, that means there's no solutions. Well, In mathematics, whenever you see a curly bracket, like these that are about to pop up, that means that the thing inside of those curly brackets is a set. Okay, that means we're representing a set, like 99% of the time. Every once in a while, you'll see someone use these as grouping symbols, but that's considered kind of sloppy because to people who do math, whenever you see a curly bracket, their brain starts thinking set, right? Not grouping symbol. So try to use parentheses and square brackets for grouping symbols. These curly brackets, that means set. So what we do is we say, we give the type of item that our set is constructed from. Well, what are our solutions to a system of equations? Well, they're points, right? Like this would be a, here, let's go back to our another example. Y equals -1/2 x plus 4. Remember this problem we looked at a moment ago? What is the solution to the equation? A lot of times people say, oh, it's a number. A solution's a number. Well, the solutions last chapter were numbers, but we're now dealing with two variable equations. So your solutions are actually points. They're ordered pairs, right? The solution here is what? 2, 3? That's our solution right there. It's an ordered pair. It's an x value along with a y value. You have to find both components in order to say you found the solution. A 2 and a 3 is our solution here, meaning that our solutions are ordered pairs that come looking something like the following. Oops, that's not right. Looks like that. There we go. So I've put in my set the type of object we're looking at. We're talking about ordered pairs. So that's the first thing that goes in there. So when someone looks inside your set, they go, oh, it's a set of ordered pairs because you're indicating to me an ordered pair. The next thing that goes in there is a vertical line. That vertical line is understood to mean such that, right? So such that means, you know, it's saying, it'll make more sense when we have the whole thing down. So this is saying our set is composed of ordered pairs such that, and then we're going to give a rule. We're going to give some type of restriction that tells us which ordered pairs are we dealing with. Are we talking about any ordered pair out there, or are we talking about a specific ordered pair? And the way you do that is you give the rule that specifies the type of ordered pairs that work. Well, think back to our problem. What did we have here? The ordered pairs that worked were the ones that satisfied these equations. So just pick either equation and write it in there. So I'll choose the simpler one, y equals 2x minus 1. Okay, so this is read as, and I should put it in math mode so it looks better. This is, so here's, we've completed it now. So here's how you would read this. I look at the curly brackets and I go, oh, it's a set. Okay, this is the set of ordered pairs, because I'm indicating the ordered pair. This line means such that. So it's the set of ordered pairs such that y equals 2x minus 1. Okay, they follow that rule. So basically what you're going to do when you do these problems, when it asks for you to give your answer in this form, the first part of this is going to look the same for you. You're just going to put an equation from your problem in this notation. You're going to put it in there. You'll just replace this equation with the equation from your problem. And this means there's an infinite number of solutions, but they all have to fit this thing right here. Okay, that's generally how those are supposed to be answered now. Okay, so, and that's this case where they fall on top of each other. Oops, like this, where the lines are right on top of each other. So this is the third of that images that you want to have memorized when you're, next week. And probably the week after that, when we're working on solving systems of equations. And like when you're doing these graphically, it's pretty clear, right? Right here, oh, I can see my lines are right on top of each other. Or I can see that I'm dealing with these lines that cross at exactly one point. Or, oh, I can see that the lines are parallel and not going to meet each other. That's very easy to see when we're using the graphical method. It's a lot trickier to see that when you're doing the algebraic methods. So when we do the algebra methods, I'll show you what it looks like when you have no solution, and I'll show you what it looks like when you have this infinite number of solutions possibility. But you want to remember these images. You want those 3 images we looked at to be able to bring those up in your head and go, oh, that's what it means. That's what we're talking about. And then you won't make the wrong conclusion, which is what some students do, right? It's a bummer when I'm grading a test, when we're doing like the long answer tests because we're on ground. I'm grading those, and I see the student do all the algebra right, and then their conclusion's wrong. And you lose like half credit, or sometimes more than half credit, because the whole point of that problem is to see if you can get the right conclusion. So it's a bummer to see them they've memorized how to do the actual calculation, but the conclusion is exactly wrong from what it should be. You lose a ton of points, and it's a bummer to take those points off. Because you kind of go, oh, this student is obviously working hard. They understand how to do this, but they messed up the conclusion at the end of this problem. Okay, so you want to know those 3 and know how to do that. So we're right at the point where I would get into the algebraic methods for systems of equations, except we definitely don't have time. There's nothing I can do in like 5 minutes that is going to be helpful to you. So next time I will pick up with the algebraic methods for systems of equations. So those of you who are comfortable with the algebraic methods for systems of equations, feel free to move right on ahead and work on that homework if you want to. Otherwise, if you don't want to, you can wait till next time, and I'll cover that material and we'll go over that. You can definitely do the graphical part. There's an assignment called Graphical. I can't bring it up because I don't want to expose people's grades, but it's called something like a Graphical Systems of Equations or Systems of Equations by Graphs or something like that. You should be totally comfortable doing that homework now, okay? And then next time we'll dive into the, it'll get a bit more complicated next time. It can kind of seem overwhelming at first, but what I find is students are actually pretty good at this chapter. It takes a little bit of practice, but once they get it, they go, okay, I can do these. And the good news is you'll get a little bit of choice. We're going to learn 2 methods for doing systems of equations, and a lot of times as teachers or as a teacher, I don't like to show multiple ways of doing one type of problem because usually it just confuses students. If I show you 2 different ways to do it, they kind of mix them together and come up with a hybrid that doesn't work. But with systems of equations, you actually need to know both ways, both for other areas of mathematics that use those 2 methods, you need to know both of them. But also because what you're going to find is we're going to run across some systems of equations where you go, oh, this is going to be way easier with substitution method. And you're going to find some systems of equations that you're going to go, this is way easier with the elimination method. So being comfortable with both of those not only will allow you to do those things in the future we're going to learn, but also it's going to allow you to do the systems of equations in the easiest way that you can. Right? Why would you want to do it the hard way when you could do it a much easier way? You wouldn't. You'd want to do it the simpler way. Okay, so I will be tomorrow going through and doing those drops for the census date. Almost all of you don't really have to worry about that because you've been doing your homework from the looks of it. Almost everybody is doing the homework reliably. And like I say, some people are behind a little bit, but that's understandable. Some people are behind a little. That doesn't mean you're not going to pass the class. If you're behind a lot, I might have to drop you, depending on how far behind you are. So keep that in mind. If you have questions that pop up, feel free to email me them, and I can address them in class next time. Right? We can start off with an example of what you're talking about, and we can look at that. So don't be afraid to email me your questions or concerns. Otherwise, I'm going to shut down the YouTube stream. As always, I will leave Zoom open as long as people want to talk to me or ask me questions, and I can assist you with any of that. Otherwise, I will see you on, is the holiday? Do we have the holiday next week? Let's see. Oh, I think I can get it from up here. Let's take a look. So you go to Ventura College, go to menu, go down to class schedule. Oops, that's not what I wanted. I wanted class calendar. Oh, did they change? Oh, here we go. Academic calendar. 21. So where are we? We are September 1st today. Oh, so Monday's a holiday. The 6th is a school holiday, so we will not have class on that holiday. So the next time I see you will actually be a week from today on the 8th. Okay? So just be aware of that. Sometimes people forget it's a holiday, and then it's worse when we're on ground. If you're at home, you just will show up, there's no meeting. But usually what happens when we're on ground is at least one person will show up and wander around campus and wonder where everyone else is. So just kind of be aware of those holidays when they come up. Looks like that's the last holiday we'll have for the semester. It's kind of right out of the gate. So, okay. So, yeah, good work. I'll stick around and answer questions.